What's going on, everybody? So, in the last episode, we talked about exact and quasi-explicit solutions to differential equations, and we acted like 19th century craftspeople. Okay, we used clever tricks and explicit formulas to solve specific equations. We treated functions then as like these smooth curves, and derivatives are like slopes in that sense. But as physics advances, we hit a wall because we encountered functions that weren't functions at all, and or Green's functions or direct delta, and we also had series that didn't converge or chaos that kind of defied or resisted the essence of an explicit solution. Right? There's no way to solve it essentially with a formula. For particularly the Lorentz attractors. So, okay, if we deal with plucked strings that have sharp corners or where a derivative can exist, classical calculus will break down when reality gets sharp. So we need a way to proceed. And we're going to leave this comfortable world of formulas, and we're going to enter the cathedral of functional analysis, and that's the subject of this video today. So what this allows us to do is stop asking what a function is at a specific point, okay, at a specific point x. Instead, we're going to view the function as a single vector in infinite dimensional space. What that basically means is we're just going to start asking what a function does to a measurement. Okay, how does it transform it? And it becomes a problem of geometry. It becomes, how is it projecting? Or what are the angles and orthogonality in this infinite dimensional vector space? All right. So this brings us to a radical shift in modern analysis because it's concerned with these more physical kind of happenings. And this is the death, essentially, of a pointwise function. So we define a function f by giving it an input x and getting an output f of x. Okay. But what Lawrence Schwartz did in 1950 is realize that this is the wrong perspective, again, for physics. He inverted the idea of this definition of a function. And so before I show you this, let's just visualize it first. So what this essentially is, if we try to, instead of looking at a function, some function f of x directly, we can actually just look at how it interacts with this blue curve called a test function. All right, and by the way, I'm still trying to figure out how to get the LaTeX to render on Plotly, so if you can help me out with that, that'd be nice. But essentially, this isn't Matplotlib, by the way. So it is essentially, it's smooth and it vanishes, outside a small region, right? And we can think of this as like a measurement device or kind of like a laboratory probe of the function itself. All right, and that's what the test function is. And so it's infinitely smooth functions that vanish outside of a compact set. Right. So a distribution T is said to be a set of linear functionals on the space, and it performs an action on the test function. All right. And it's not a function that you can plot directly because it's a linear operator that eats this test function and spits out a number. And this T here is that number. And we're going to write this as its pairing as such. And so the most famous example of this is the direct delta function, which is a function that disappears into a vertical line. And so that's essentially, if we have the test function and we take the limit as this epsilon gets really, really, really small, it becomes, it takes on a value, right? And what this allows us to do is evaluate the test function at 0, okay? And that's essentially what the direct delta function tells us to do. Now, this isn't really a function at all, right? It's kind of an abomination, but it is defined as a it is well defined as a distribution itself. Okay, and so it's going to evaluate, while remaining this compact set of test functions, or it satisfies the compactness that's required for it to work. And so essentially all of these test functions here, when they're evaluated at single points, they give us this nice property as well. Okay, now this new definition really gives us a superpower, this definition of the distribution, because we can differentiate things that aren't differentiable now. And so the reason we can do this is because classically with a function with a corner like a triangle wave, it has no derivative at the tip of the triangle wave, but in the world of distributions, we can steal the derivative at that point from the test function by using integration by parts here. Okay? And what this means is, since a test function is smooth, we can define the derivative of our rough distribution u right here by just passing the derivative onto phi, because it contains something called compact support. So this allows us then to do calculus on shock waves or cracks in materials and quantum jumps, because phenomena where classical smoothness essentially forbids the physics from happening is avoided, or it's not really avoided, but it's kind of extrapolated from this. And it's a way, this is really the gateway to weak solutions, which we'll explore next. So distributions, again, gave us the freedom to differentiate anything, but they're kind of wild, right? They contain objects like the derivative of the direct delta or whatever, and that has infinite energy. Okay, so physics requires limits again. So we're going to need a space that allows us that is rough enough to allow corners, but smooth enough to allow finite energy, and that's what is coming in to the picture, which is Sobolev spaces. Now, the most important space in quantum mechanics is L2. Okay, and L2 is a special case of a Sobolev space, which is the Hilbert space. Okay, and in L2, functions can be discontinuous. They can jump, but to do partial differential equations or to solve regular differential equations, we need derivatives, and we need to define the Sobolev space as H1. Okay, and this is the club for functions that are in L2. If that makes any sense, and whose weak derivatives are also in L2. So let's look at this curve here. We can arrive at this jagged curve. It's like a stock market chart or a Brownian path or whatever. It has no classical derivatives at any of these peaks, right? But it does have a weak derivative with finite energy. And this is the natural home for solutions to the heat equation or the Schrodinger equation, because what it does is it bridges the gap between the impossible smoothness of calculus and the gritty reality of physics. And as you can see, we can make it even more rough and rougher, and we still see the existence of that weak solution. We can extrapolate it out and understand it more, versus in H1, where we have the continuous derivative in L2, and essentially allows us to solve it weakly and solve it as a continuous in the continuous form as well. Okay, so again, for defining the space of square integral functions, we are equipped with this inner product, and this inner product space then allows us to control the derivatives. And again, that Sobolev space is a space of functions whose weak derivatives are also in L2 or in the Hilbert space. And so this allows us then to just define norm measures as some kinetic plus potential and bound it, okay, or describe the norm measure. And the Sobolev embedding theorems just tell us when those weak functions are actually continuous, linking energy to the idea of regularity. All right. Now let's talk about spectral theorem. We discussed this previously in the initial conditions series. And again, what did we do here? We just assumed that we could expand any solution into sines and cosines, but why does that work? And why do the functions form a basis? Why can we do Fourier transforms? Or why can we do Laplace transforms that we assumed in the previous episode? And the spectral theorem gives us this because in finite dimensions, a symmetric matrix can be diagonalized. And in infinite dimensions, a self-adjoint operator, like this Laplacian here, which is an unbounded operator or an unbounded operator in L2, but in the compact domain, it can be decomposed into eigenfunctions, okay? And allows for us to spectrally decompose it. And this also motivates Sohn's theorems and semigroups, but I just kind of want to show you that when we strike kind of a mathematical drum in space, it vibrates at specific discrete frequencies, and these are the eigenvalues, okay? And so the standing waves, or these eigenfunctions, are really the atoms, if you will, of the function space, because they are, that was eigenmode 3, but they're orthogonal to each other, and the spectral theorem guarantees that any valid physical state on this domain can be built by, essentially stacking these particular waves that I'm showing you, or the spectral expansion of these waves, and stacking them on top of each other. And this is the rigorous justification for Fourier series and quantum mechanics. So we can play around with these particular eigenmodes here. Here's the circular. Let's look at the circular domain. It'll look a little bit different. This is a square domain, but in the circular domain, sorry for the bleeding on the edge here, but you can literally see the mesh. But that's what the circular domain looks like here. All right, and for different, and again, all of these are orthogonal to each other, all of these eigenmodes. And let's look at, I can't remember what this other domain that I use. It might be like an L-shaped domain. But yeah, of course. So this would be like an L-shaped domain. And again, there are eigenmodes, or eigenmodes that are defined. And solutions can be, again, combinations of these of this basis, okay, of this complete set of basis vectors that span a solution space. So again, we get the idea of the self-adjoint operators comes back from our initial conditions, and Sohn's theorem also, for time-dependent problems like the Schrödinger equation, we need to exponentiate operators. And we would say that an operator, that if H is self-adjoint, and if it generates a unitary group of time evolution operators, it establishes a one-to-one correspondence between the physical observables and the Hamiltonians and the time dynamics. Again, this guarantees that the eigenvalues are real. We can actually measure them, okay? And so that's essentially the power of the spectral theorem. Now, again, if we arrive at some of the conclusions, or if we take the conclusions and try to arrive at something even more powerful, we can try to prove that the solutions exist using variational methods. So instead of trying to solve an equation point by point, we can actually turn it into a minimization problem, because nature happens to be really lazy, all right? And it seeks the energy, or it seeks the state of lowest energy. And so if we can imagine a space of all possible functions on an infinite landscape, we can define an energy functional, right? So if we could, first of all, if we consider the Poisson equation with the Laplacian acting on a function, right, to give us this homogeneous solution, we can multiply a test function and integrate by parts to give us the integrals over the space. And this is precisely what we call the weak formulation, which says that if we have a function in the Sobolev space such that we have some a of u comma l for l of v, u comma v, and for other functions in the Sobolev space, where a, essentially, this is a bilinear map that's representing the internal energy, we can then this will allow us to get the weak solution. Okay, and by doing this, essentially, it's just the integral by parts, but extended for not just distributions, but restricted towards finite energy spaces. We can then have the Lax-Milgram theorem, which tells us that this is really the fundamental theorem of linear PDEs, and it states that if the bilinear form A is bounded, and if it's coercive, which means that the system, again, has positive energy, the unique solution, or a unique solution exists, and this replaces specific integration tricks with just a universal geometric argument about the energy functional in some kind of projected space. So we can construct some energy functional J of U, and again, for PDEs, this landscape looks like a giant infinite dimensional parabola, or a paraboloid. And what the Lax-Milgram theorem tells us is that the most fundamental result is that if this bowl is coercive, which means that if the slides go up steep enough, there's exactly one marble at the bottom of this surface that is our solution. So we don't need to find it by calculus itself. We can just find it by geometry. And what that means is this geometric view is exactly how computers solve partial differential equations, because we can't handle the infinite dimensions in code. So we project the problem onto a finite subspace, and that essentially necessitates then Galerkin methods. So the Galerkin method, before I go through all of this, this is how you look at it visually. So we can see that there is a true solution in blue to the differential equation that is necessitated by the geometry of the energy functional. What we can do is actually try to approximate it with piecewise finite elements, because we have computers, right? We can actually we can't do infinite dimensions in our computational spaces unless you're quantum computing or something. But again, that's also just another way to approximate the true solution in the abstract kind of sense. So these approximation, the approximation snaps to this blue curve, but if you look closely at the error, the gap between them here, the gap between them and trying to graph the error itself, the Galerkin method ensures that the error is orthogonal, if you can see that. So the error itself is orthogonal to our building blocks, and it is the best possible approximation given some limited resolution. And this simple geometric idea of orthogonal projection of error is the engine behind the finite element method that's used to design, airplanes and bridges and stuff, because error is orthogonal, we can do our best to try to abstractly solve the differential equation by using the Lax convergence theorem. So again, what we do is we take a finite dimensional subspace of the Sobolev space mathematically. So these would be like piecewise polynomials, and we just approximate a solution, or we seek an approximate solution within that subspace that turns the PDE into a matrix equation. And the error then, again, it's physically significant because this satisfies the Galerkin orthogonality condition. So that essentially means this orthogonal projection of the true solution is projecting itself onto the computational subspace with respect to the energy inner product. Okay? So that's the rigorous justification behind this. The last thing we're going to cover is the solution unique? So for many operators, the answer is no, because we classify operators using something called the Fredholm index. This integer counts the difference between the number of solutions and the number of constraints. So it becomes a topological solution on the test function space, because what we can do is perturb the operator and mess with the parameters, but the integer will not change, or the index. And so this is our first hint that analysis or functional analysis is not just about calculus, but it's actually about topology, or the number of solutions really depends on the shape of the topological space that defines this space of test functions. Okay, and that's essentially what solvability and Fredholm theory allows us to address. So we've built the cathedral of functional analysis. We have rigorous spaces and energy functionals and spectral bases to solve differential equations rigorously, but we're still stuck in flat coordinates. So in the next episode, we're going to break free from the grid entirely, and we're going to learn to do calculus on curved spaces, where derivatives become covariant and geometry then will dictate physics. So I'll see you guys in the next episode.